In this lesson, we're going to be looking at interlocks. And interlocks play an important part in all PLCs. It's how you control whether or not you're outputting something, whether you're moving on in a sequence step, and things like that. So we need somewhere that is easily accessible, where all of our stuff can sit together in the same place. There's really no sense in keeping our interlocks in asset data. They can be derived from asset data, and they should be derived from asset data, but actually keeping the interlocks in a particular asset means that you're scattering your interlocks everywhere. What's more beneficial is to have a UDT that is then sitting in this interlocks area, and then you can just pass that one common structure, your interlock structure, across any data block, any function block or management system that you need to access and write interlocks in. So with that being said, let's just have a look at what I mean by an interlock. So in our scenario that this course is built around, we're going to be looking at creating a SAM filter. In order for us to do particular sequences and to start certain events like opening a valve and things like that, we need to be careful and mindful of the state of the rest of the filter and the assets that make up that filter. So, for example, we wouldn't open the backwash valve here if the sequence wasn't enabling us to do that. And we do that through output controls, through writing to AVO3's data to say we are requesting the backwash valve to be opened, but it works the other way around as well, which is we would never enter the sequence that opens the backwash valve if we already know that this backwash valve is failed. Now, if your sequence touches every single asset, you would have to bring in every single asset into that sequence, which doesn't make sense, and sometimes it's not possible if you have many assets on your sequence, because there is a limitation to how many interface pins you can have on a function block. And remember, we are passing everything through interfaces, so we have to be mindful of the fact that we can't just keep growing and expanding our interface. Eventually you hit the limit, which I think is 100 pins on a function block. You will hit that limit, and then Tier Portal will say you can't add any more to this function block. So what we do is we reduce down into a interlock UDT. So we create the status, which we've already done in this asset here in the quarter turn valve asset data that says whether it's failed to open, failed to close, or whether it's unhealthy. And we then write that to an interlock. So we'll have a look at that now. So the first thing is to create your UDT. So if I come down to data types and I create my UDT interlocks, I will give this a more definitive name and call it filter interlocks, just because as projects grow, at the moment this is just one filter, and that makes sense. But this could be part of a wider system where this PLC has interlocks that come from another layer over comms, for example, and then you might want to expand on having an additional UDT for comms driven interlocks and things like that. So, and then if we go back to our interlocks here, I'll just split the screen. So we have UDT on the right and our interlocks here. I will call this filter and point it to UDT filter interlocks. It will moan at the moment that there's nothing in there, which is fine. And then if we go back and have a look at what I was talking about here, so AVO3 backwash valve, we need to know that that valve is healthy, which we can check directly. But for a normal filtration sequence, what we need, so we're in filtration at the moment, this is the example that we're looking at. If I wanted to go into filtration, the backwash valve could actually be failed as long as it's closed, and we know that it's closed. Then we could open the inlet valve and the outlet valve, and as long as the flow meter is healthy, turbidity monitor is healthy, the outlet valve is healthy, and the inlet valve is healthy, differential pressure is healthy, and the filter level is healthy. As long as all of those are healthy, then we are okay to start the filtration sequence. So now we can start bundling stuff down into single booleans for interlocks, rather than us checking every single time that we need to check, is everything for this sequence okay? We can start grouping that stuff together in an interlock manager, and that interlock manager takes in all of the data that we need, or accesses all of the data that we need to access, and amalgamates everything down into a single interlock. So, for example, I would have in here sequence filtration, okay to start. And then that's just a standard Boolean. If I update the interface on here, we now have that in there. So sequence filtration, okay to start. We now need to drive that with a signal that says that it's okay to start. And we can do that if we come and have a look at main here, and I'll just unsplit the screen. We have filter control in our main OB, in our OB1. If I come into filter control, what the filter control's job is to do is to create all of the statuses and all of the control elements required to facilitate the main control. So this will be making sure that everything is ready for status-driven stuff on SCADA and the HMI, making sure that our interlocks are created correctly, and we have a filter data here, which we'll go into as we go through examples, but we now need to add in our interlocks. So filter interlocks, UDT, filter interlocks. And that gives this block access to the interlocks now. So now what we have is our filter data, which we haven't been through yet, but is everything internally to do with this filter. And I know that the assets are sort of internal as well, but it's more control elements. So if we were to look at what we're doing here, we have time passed since the last wash and shut down on max wash time. So we're looking at time passed since a particular time. And if it goes over the max time since last wash, or if the number of days is over 20, then we say you must shut down on no wash. And that is like an event that would be raised, and we would action that. So it's very similar to an interlock, but it's not being driven by an asset. It's not coming from a piece of physical equipment. It's control derived. So you could put that information in the interlocks if you wanted to, but I quite like to keep stuff separate and know that my interlocks are always from like a physical device or from a communication layer or something like that. They are generated by something actually happening, or something that you could go and look at. Whereas software stuff sits inside the data because it's just time period that's passed, or a particular software derived event has happened, like a button press on SCADA, for example. It's not quite the same as saying there's something really wrong here. We've lost an analog signal from an instrument. So in this block here, this is where we would write the interlock to say, so sequence filtration okay to start. And if I create a new line, this will be where we start to see we need to bring information in. And just bear in mind that if function blocks do get too big, I think we discussed this in a previous lesson, that you can access global data on the first layer of function blocks. So, for example, let me just demonstrate what I mean. So we're in OB1 at the moment, and in OB1 we are accessing data that's global, and this data is global. So filter data is this block here. If we found that actually there's quite a lot of stuff on this interface and it's not reusable, we're not looking to make this a reusable block. It's a management area, such as like sequences and things like that. It's only ever going to be called by an OB. It's never going to be nested inside something else. Then that is okay to then come into this block and access this sort of data directly. Just bear in mind that you won't be able to add it to a library, but then it should be bespoke for that project anyway if you're calling it in the first layer like that. And as the project comes together, we'll see how that stuff sort of comes together in itself, and it'll paint a better picture of what I mean there. So I'm going to access the interlock data through the interface, but I'm going to access the asset data directly because it's only ever going to be used in this project. So before we dive in and update that logic, let's just remind ourselves of which valves we're looking at and what instruments we're looking at. We're looking at AVO1, MVO2, which is modulating valve O2, the turbidity monitor, flow meter, and filter level. All of those, and the differential pressure, sorry. All of those must be healthy in order for us to run in filtration mode. So I should be able to come here and say AVO1 typed control status healthy. So the valve must be healthy. And I can do the same with instruments as well. So IL01 typed alarms. We're only interested in out of range. You could update this function block to produce a healthy status, but typically I don't produce a healthy status for an analog instrument because the healthy status is it's either in range or out of range. There isn't anything else. Some devices might give you a Boolean to say healthy, in which case you can factor that in. But typically you just have you've gone out of range, which happens when the unit goes off, which happens when the unit has a problem, or has gone open circuit, or anything like that. So that's why I'm using out of range. And it would be that way around because it's an alarm. And basically you just build it up like this. So you'll end up with something along the lines of this, where we have the check for AVO1 being healthy, MVO2 being healthy, and then all of the instruments that are required. So the level instrument, the turbidity instrument, flow meter, and the differential pressure. All of those need to be healthy in order to even start our sequence, because we know that if one of those isn't healthy, we can't run in that sequence mode anyway. So with that being said, this would be where we go to filter interlocks and then go to sequence filtration, okay to start. And it's okay to just leave that status sort of running all the time. Our interlock will come on and off as and when situations change, and we know that we can check that interlock at the point of starting our sequence, and we could even potentially check that interlock at the point of shutting our sequence down. So if we start the sequence and that's on, and we see that filtration okay to start come off, we can then shut the system down. However, what's probably more likely is that we will use the actual data coming from our assets to determine why and when we shut down, because there's a difference between checking are we okay to start, and even though that asset's failed now, are we okay to continue? Starting from a unhealthy position is not the same as something going wrong once all of your valves are in the correct positions and things like that. So we'll cross that bridge as we go through examples later. But what you can do now is systematically go through this this drawing here and the sort of control philosophy and work out what all your interlocks are. And sometimes you'll have individual interlocks. Sometimes you'll have that only sort of look at one thing. So it might be, for example, if we're in no filtration situation, if we're in, let's pick this one here. So air scour, for example, if you're in an air scour where we're pumping air through the system, like in reverse to clean the filtration media, this orange filtration media here, and our level fails, well, do we need our level during that phase? So by having a interlock layer or a management layer that manages the interlocks, we can then make things very easy for ourselves later by doing all of the filtering and all of the conditioning of those interlocks up front before they're required in our sequences, and then we reduce everything to just one Boolean value that we're checking, which is much better than what I sometimes see with other people's programs, where those interlocks will be in the middle of a sequence, and you might have some complicated timing or looking at lots of different variables or sort of ranges on analog signals and things like that, that then determine whether or not you're allowed to move on to the next step, when actually those conditions are nothing to do with the sequence. They're just checking them because they're at that point in the sequence. Having an interlock management area where you manage the interlocks and you sort of take the fluff of the sequence away and just look at what drives the interlock makes things much simpler and much more easier to follow in your sequence later. So just a quick recap, we should end up by the end of this project with a interlocks layer. We're using a UDT because if we're using a UDT, we can stick it on an interface and it's nice and easy. If the UDT is updated, so is the interface. Everywhere it's used in our project. That makes that nice and easy to use. And the interlocks will be managed up front, outside of the sequence and things like that in our block called filter control. And when we go through the end of the sort of project, we'll refactor some of this. So you might find that some of these rungs end up in functions just to make things grouped and nice and easy to follow.